So let's turn to our next special topic, and that's accelerating clocks in Minkowski space. Okay, so the issue we want to address is special relativity, and we want to ask, can special relativity apply to all motions in flat Minkowski space? I bring this up because I hear all the time from students and from physicists that if they have a problem in acceleration, they think they have to bring into bear general relativity. They think that special relativity only applies to velocities which are constant in time. Okay, well, I can understand the confusion there because, as you know, if you're given an inertial frame, then any frame in relative constant velocity motion is another inertial frame. That's one of the premises of special relativity. Okay, but what does relativity really apply to? And what does general relativity apply to? Well, first, as we've learned, general relativity is the theory of gravity. Okay? General relativity is the theory of gravity. Okay, it tells you how gravity deforms space-time and makes it curved. Okay, and therefore we develop gravity as a way to express the unification of special relativity, okay, with Newtonian gravity. You have to come to a theory of what's called general relativity, where you have gravitational forces that that respect the equivalence principle, okay, with the principle of special relativity, okay, that respects the fact that the speed of light is a speed limit in any inertial frame. Okay, and so you learn from the work of Einstein that the way to embody that into a theory is to generalize the idea of a metric, okay, from Minkowski metrics, flat metrics, to curved metrics, and to encompass the gravitational forces actually as an apparent or virtual forces as the curvature of space-time. And we've learned that many times now. Okay, so that's what general relativity is. General relativity is the theory of a space-time which is curved. But what is special relativity? Special relativity is the theory of a space-time which is not curved. Of course, it's Minkowski space-time, as we've learned. Okay, we learn about Minkowski space-time, and then we learn that boosts, Lorentz boosts, leave Minkowski space-time invariant, right? The g mu nu of Minkowski space-time is +1, -1, -1, -1, okay, and boosts in any direction leave it unchanged. But that doesn't mean that you can't describe accelerated motion in it. It just means that the space-time is flat. Okay, but the motion of a particular particle will be whatever it is, and you'll describe that with special relativity. For example, in special relativity, that's the era or place of Maxwell's equations. And in Maxwell's equations, you have accelerating charges that radiate. So the charges, of course, are not of a fixed velocity. They're whatever they are. And remember, when we derived the Maxwell equations, we began with Gauss's law. Okay, and Gauss's law states, okay, that that the source of the divergence of the electric field is the charge. Okay, but then we wrote that as a differential equation, okay, which said that the charge at a particular space-time point is the divergence of the electric field at that space-time point. It doesn't matter what happens before. It doesn't matter what happens after. Okay, it's a local causal differential equation. Okay, and so any possible motion satisfies Maxwell's equations, and Maxwell's equations, the only restriction is that Maxwell's equations are then written in Minkowski space, or flat space-time. but we learned in general relativity how to write Maxwell's equations in a curved space-time as well. So that was easy for us. What the breakthrough was, was to write Maxwell's equations as a differential local equation for any motion whatsoever. What we had to lean on at that point was the experimental fact, that the charge, of a particle is invariant under any possible transformation. So we have the charge of the electron. It's a certain number. We measure it in its rest frame, and then we measure it in a frame in which it's moving with a constant velocity. We get the same answer. We move it in a frame of reference that has a constant velocity and an acceleration. We get the same number. We move it in a frame of reference in which it has a constant velocity, an acceleration and a jerk, and you get the same number. From that statement, then you write down Gauss's law in general, that the divergence of E is equal to the charge density at that space-time point, no matter what the motion is. And then you get Maxwell's equations from that, as we did in the first 1/3 of this course. So that's the idea, that's the idea. Special relativity applies to any motion whatsoever, as long as it's in Minkowski space. There's a lot of confusion because I think it's really because of those textbooks that always insist on looking at special cases where the motion, that generates the electric field or the magnetic field is either at rest or at constant velocity. But that's just child's play. We got over that. We understand that really the basis of special relativity, the basis of electrodynamics, the basics of general relativity is local causal differential equations. And there you look at what's happening at a space-time point, point by point, and then you can formulate the theory appropriately. So we do that here. Special relativity can apply to all motions in flat Minkowski space-time. That's its restriction. Why? Because its particular equations of motion contain all such accelerations, jerks, etc. But it is the theory of flat space-time. So let's take a look then at accelerated motion in special relativity. We'll do this exercise. We'll discuss the twin paradox again. We'll discuss accelerated frames of reference. We'll generate the Rindler space-time. We'll discuss the equivalence principle. There's a lot to do, and a lot of it's very interesting, and I hope it clarifies the point that I'm ranting and raving about. So I want to consider a clock C prime. It's accelerating in an initial frame S. At a time t, it has velocity v of t. See, it's accelerating, but at a particular time, it has a particular velocity. So at that particular time, at that particular velocity, I look at locally at that accelerating clock, and I read off its measurements from the point of view of an inertial reference frame, which at that particular moment has exactly the right velocity to match its motion. So I'll let S prime be C prime's instantaneous rest frame at the time t. So here it is. It's at rest at the frame S prime. S prime is moving at a velocity v of t with respect to my good old frame, this frame here, which is inertial, and the clock C prime, in our application, is going to have a proper acceleration g. That means the acceleration with respect to S prime at all t prime is given by g. So that's the problem that I want to consider. So I want to consider the movement of this clock, and this clock is accelerating. And I want to understand the measurements on this clock, its time relative to my time. And I should be able to do that because it's moving in a Minkowski space, and that's a problem of special relativity. So we recall from the first third of this course how to transform acceleration from s prime to s. Okay, so I just look up in our previous formulas, okay, that the acceleration in the x direction, I have a boost in the x direction, that's the direction of my velocity, okay, that a prime of x, a prime in the moving frame is related to a in my inertial frame by this formula here, gamma cubed, and then a term here, which is our standard term, which looks like the relativity of simultaneity, as we've seen again and again. Okay, but now I want to take a special case. I don't want to deal with the problem in general. I want to consider a clock which is at rest in the frame s prime, and the s prime is executing a velocity which is dependent on a time t. So it might be accelerating at a particular time. Okay, if it is so, okay, then s prime will be the inertial reference frame which matches the velocity of the accelerating frame at that particular time. Okay, so for example, I take a prime of x to be equal to g, a fixed proper acceleration. That means in the frame s prime, it's not moving. The clock is not moving. U prime is 0. So this term is absent. Okay, and so the acceleration in my frame x, dv by dt, that's acceleration in the frame x, of course, by definition, is equal to a prime sub x, I'm calling that g, divided by gamma cubed. Okay, and so there you have it. There I know, therefore, how to transform my time from one frame to the other. I learned, in fact, that dt is equal to 1 over g gamma cubed dv, where dv is the change in the velocity. Okay, what I'm really interested in, okay, that's a step in the right direction, but I really want to know the relationship between t, okay, the velocity in the frame in which the clock is instantaneously at rest, okay, to the no, that's the time of my frame, my inertial frame, and I'm looking at a clock which is moving by. I want to relate that time to the time of the clock. It's rest frame time. I'm going to call that d tau. Okay, so consider the time on the accelerating clock and the time on the clock at rest in s. Okay, well, if they're moving at a relative velocity of v, I know that the times on those two clocks are related by time dilation, and that's what I've written down here. d tau is equal to 1 over gamma dt. Okay, time dilation at that particular instant. Okay, at a later instant, the velocity is different, and so I'll have d tau equal to 1 over gamma dt, but gamma depends upon t itself through its dependence on v of t. Okay, so that's easy enough to deal with. Okay, so let's take this equation, okay, and this equation, okay, and bring them together. Okay, this is from the acceleration of a clock at rest in s prime. This is just the general time dilation expression. I can get rid of dt on both sides of the equation, and therefore relate d tau, the proper time registered on the moving clock, in terms of its velocity as measured by me in the inertial frame. Okay, so the price I pay is a gamma downstairs, there's a gamma cubed upstairs, so I get d tau is 1 over g gamma squared v. Well, that looks a little bit complicated, but not so bad. Gamma as a function of v, I know it, so I can integrate this thing up. Okay, so integrate this equation and get tau as a function of the velocity. First step. Okay, so tau, integral over d tau, just take this thing here. 1 over g is a constant. I'm imagining that the clock is accelerating at a constant proper acceleration g. And here I have dv upstairs, gamma squared, that gives me a 1 over 1 minus v squared of c squared downstairs. That's a standard integral. It's just the log of this expression over here. Okay, so tau is equal to c over 2g a log. Well, I want to get rid of the log, so I'll exponentiate the whole thing, okay? And so I'll get v of tau, right? V is a function of tau. Tau's on my left-hand side, as written down here, okay? Okay, so I just integrate the things up. I have a logarithm here, so I have an exponential here when I put the logarithm on the other side of the equation. I exponentiate this equation, right? I take 2gc, throw it on this side of the equation, then I exponentiate, so I get e to the 2g over c times tau, okay, is equal to 1 plus v over c, 1 minus v over c, and I've just written that down over here. Okay, and so that's easy enough, and I get the ratio of these two exponentials. I fiddle with it a little bit. I see that it's the difference of exponentials over the sum of the exponentials. That's the tanh of g tau over c, and so I get my solution. Okay, and so I find v as a function of tau. Okay, so the clock is accelerating with respect to me, and its velocity is increasing as a function of time. I'm solving for its velocity as a function of the proper time of the clock, and it's accelerating. So it's going to go from a small velocity to the maximal velocity, the velocity of light. And how does it do so? Well, it does so, I learned from doing the integral, as c times tanh of g tau over c. Tanh ranges from -1 to +1. So when g tau over c becomes large, tanh goes to 1, and the velocity of the clock goes to c. And that's exactly what I expect. Okay, that's perfectly sensible. So here, just do this little bit of arithmetic. Remember when I take this term and I exponentiate it, I get e to the 2g tau over c is equal to this ratio, and I solve for v over c, and I get v of tau is equal to this ratio over here, and I clean it up and I get tanh. Okay, so we're going to find hyperbolic functions in all of this because of this arithmetic. Okay, it's not so mysterious. It comes back to the fact that this integral is just a logarithmic integral, and so it leads to logarithms, which lead to hyperbolic functions, which lead to exponentials, which lead to hyperbolic functions. And there you go. Okay, and this result makes a lot of sense to me. Okay, I accelerate the clock, and eventually it gets as close as possible to the speed of light. Okay, now I can continue with that. That gives me my v as a function of tau, but I want to know other things. I want to know the time as a function of tau. I want to know the position as a function of tau, and I can get all of that now because I've gotten the first step. In particular, gamma is my standard formula, but I just learned that v goes like tanh, so I put that into the formula. Okay, and then I end up with 1 minus tanh squared to the -1/2. Okay, and then I remember a little bit of hyperbolic geometry and see that this quantity, 1 minus tanh squared to the -1/2, is cosh. Okay, the hyperbolic cosine of the argument. So I can take that and then substitute into my equation, okay, which means that back here, you know, the relationship between dt and d tau, which was just the time dilation. Gamma is a time dilation, it's a cosh. Okay, so dt is equal to a cosh times t tau. That's just the basic time dilation of special relativity. There you go. Okay, and I can integrate that up on both sides. The integral of dt is t. Okay, the integral of cosh is sinh, and there you go. Okay, watch your factors immediately when you do that. Okay. So again, look at supplementary lecture 11. Okay, that goes through some of the details that we're passing over them quickly because we're emphasizing the concepts here. Okay, so I have a relationship between t and tau. Okay, okay. So t goes like sinh of tau. Now remember that sinh is a hyperbolic function, which for a large argument goes like an exponential. So the relationship between t and tau is exponential, okay, for large tau, and that's going to be interesting in our application. But in general, that's the result. That's the end of it. That's the result. No approximations. Finally, I can find x as a function of tau. That's what I want. I have t as a function of tau. I want x as a function of tau, so I can plot the position of my clock on a Minkowski diagram. Well, the position of my clock is related to the velocity times dt integral. Okay, this is just the statement that the velocity is the rate of change of the position of the clock in my frame, in my inertial frame. Okay, so I just integrate it up. I have to integrate v dt. Well, okay, so I look back. V goes like c tanh. Dt goes like sinh, like that. Okay, goes like sinh, and so dt goes like cosh. I go back to this expression. I need dt, not t. So I go back to this expression, cosh, d tau. I watch my factors of g over c. Okay, now tanh times cosh is sinh. Okay, just doing a little bit of hyperbolic geometry here. Integral of sinh is cosh, and I'm done. So there you go. I have the position as a function of tau, okay, where my initial position I'm saying is just c squared over g. That's the simplest possibility of it. Okay, so now I have x as a function of tau. I have t as a function of tau, and I can look at that and plot that on a Minkowski diagram. Okay? Well, the first thing I notice is if x goes like cosh, t goes like sinh, then if I square each of them and take the difference, I get a constant. Okay, I get x squared minus c squared. T squared is c to the fourth over g squared. G squared is the proper, okay, acceleration of the clock in the moving frame. Okay, and so there you go. So the clock moves on this hyperbola like this, and I've shown a point A where it's initially at rest with respect to my inertial frame, and then it moves to the point B where it has a certain velocity. I notice that when t is equal to 0, x is equal to c squared over g, and I've written that over here. Okay, I remember Lorentz. Okay, so this moves on an invariant hyperbola, and that's very important. Okay, the clock is moving with a constant proper acceleration. That puts it on a hyperbola, and the hyperbola is an invariant hyperbola. What do I mean by that? I see that x squared minus c squared t squared is a constant. That's what I mean by invariant hyperbola. Okay? Invariant hyperbola. So in any frame, right, it's going to be x squared minus c t squared is equal to that constant, because that's an invariant. Okay? X squared minus c squared t squared is an invariant. It's invariant under Lorentz boosts. I just get this constant c to the fourth over c squared, like that, right? So it moves along this hyperbola at the, okay, so when t is equal to 0, okay, x is equal to c squared over g squared. So it sits there, okay? Okay, and it sits there with no velocity, right? So that the rate of change of the hyperbola points in the vertical direction. Okay, then it moves along this position, it gains velocity, it's being accelerated at a proper acceleration of g. Okay, so it gains velocity, and at b, it's curved over here like that. Now eventually, okay, if it experiences a constant proper acceleration, it's going to eventually get a large velocity. The speed limit is c, and eventually it will become tangent to the light ray shown here, x equals ct. Okay, So remember, on the boost, the points shift along the hyperbola, okay, because it's an invariant hyperbola, and when it's boost, we'll just preserve that fact. Okay, because of the hyperbolic functions, the disparity between t and tau can be amazing. So I just plotted that out here. Here's GTC on one side, and here's G tau C on the other side. Okay, they're related by hyperbolic functions. Okay, and so I've written that out. I've written that out here, where my G tau over C is a relatively large number. Okay, and so my sinh of G tau over C is essentially just the half the exponential, and so it grows exponentially. I plotted the right-hand side in a logarithmic fashion, okay, and the vertical side in a linear fashion, and so you see it there. And that's approximately quantitative. I say approximate quantitative because I just draw it here on this figure, but then the figure in supplementary lecture 11 is quantitative. So take a look at it. From the formula, I see that V of tau, which is equal exactly to C tanh of G tau over C, is equal to this expression when G tau is very large. Okay, it's C with small, exponentially small corrections in tau. There are power behaved corrections in T. Okay, and so I can relate the logarithm of GT to tau with a constant. Okay. And so now I understand it. I have a clock which is accelerating with respect to me, okay, at a constant proper acceleration. Okay, it achieves an enormous velocity with respect to me, very close to the speed of light. Okay, after a certain amount of time, I view that off my graph. Okay, and so the time dilation between its clock and my clock is very, very large. Okay, and that's the origin of this disparity. Okay, between the time taken on the clock, moving in the accelerating frame at almost the speed of light relative to me, with respect to me sitting here and looking at my eye clock. Okay, and here are the details that I've just written down. Okay, well this gives us an opportunity to go back to the twins. Okay, we can take the twins and imagine that Maria isn't stuck on an old-fashioned rocket which only goes at a constant velocity. We can stick her on a rocket, okay, which moves with a constant proper acceleration in one direction or the other, and see what happens. So here I'll imagine that Mary sits at home, okay, and she does so for time t, 2t, 3t, and 4t. And then Maria goes on a closed path. Okay? So she accelerates to the right with a proper acceleration g. Okay? Okay, like this, up to a proper time tau, which corresponds to the time t. Okay. At that point, she's a distance x of tau away from Mary. Okay. She doesn't want to get too far away from Mary, so she reverses her rocket thruster, and all of a sudden moves with an acceleration of minus g back to Mary. Okay, so if she had a velocity v of tau here after time tau, after time 2 tau, she's at rest with respect to Mary. Okay, at a position 2x of tau. Okay. And here it's shown. Okay. But she's still far away from Mary. She wants to get back to her sister. She wants a closed path so we can execute the twin paradox. So she continues with an acceleration toward Mary, minus g, okay, and gets to the position 3 tau. Well, okay, so at that point, she's still a distance x. She's a distance x from x of tau from Mary, okay, and she has to get back to Mary, and she wants to be at rest with respect to Mary. Okay, so she's been accelerating here with an increasing velocity here. Okay, a decreasing velocity here, a velocity which is minus v of tau over here. So she wants to get to rest. We reverse the Mary. So she reverses her thruster and puts the thruster, so she has a proper acceleration g in the positive direction. So after another interval of tau, she ends up at rest back to Mary itself. Okay, as you see in the picture. So Mary's strip is closed. Her proper time at the end reads 4 tau, and Mary's time reads 4t. Okay, where t is related to tau by the hyperbolic sinh function. The thing that's interesting about this little calculation, well, there are two things. First of all, the velocity is a continuous function of t or tau, just shown here. So it's rather different than our initial discussion of the twin paradox, where the velocity changed essentially discontinuously when Maria jumped from an outgoing rocket to an incoming rocket. I don't have to get the twin paradox in that particular configuration, although that is the most instructive thing to do. Okay, I can do this one instead, where the velocity is continuous, the acceleration is not. Okay, but the velocity is continuous, and I can look at my lines of constant time from Maria's perspective and understand the disparity between the time t and the time tau. But I haven't shown that here. Okay, note that v is a smooth function in this example, and I notice that t is related to tau by a cinch. If g tau c is very large, it's an exponential difference, and so I can get a huge disparity in the twin paradox. Okay, where Mary she ages by t, and Maria ages by tau, and there's almost an exponential difference between the two, and that's a nice illustration of the twin paradox. Okay, so I certainly like that case. Okay, so we're looking at uniform proper acceleration, and here I've shown it again. We want to just concentrate on it and understand it. So I imagine a rocket taking off at t equals 0, and I'm imagining taking off at x equals c squared over g, like that. And it's traveling on a hyperbolic trajectory like this. These are, the clock having a constant proper acceleration followed the path of a hyperbola, and the hyperbola is a invariant to Lorentz transformations. That's its critical property. It's an invariant to Lorentz transformations. Okay? X squared minus ct squared was a constant. Okay, that gives the simplicity to the problem. It's like the path for light. Okay, that's an invariant. C is the same in all frames. Okay, this hyperbolic motion is the same in all frames. Okay, and so I can ask certain questions of it to get a better appreciation for it. For example, here I can start off at the point A, and I can have a light ray over here, and I can start accelerating on my rocket ship from rest, okay, with a constant proper acceleration to the point B, etc., up here. And the light will take this trek over here. And I see from the picture that light can never reach the rocket, okay? Light moves at the speed limit, but it can never reach the rocket because the rocket has an advantage by being at a position c squared over g to the right. It can never reach the rocket, and I can calculate the distance between them in a frame S. It's just x minus ct, right? So I just want to calculate x minus ct as we move up the frame, okay? As we move up here in the frame S, eventually I see that the distance in that frame is going to go to 0, but let's see how it works. The invariant hyperbola is x squared minus c squared t squared is equal to g fourth over g squared. I can write that, I can factor the left-hand side like that. Okay, I want to understand x minus ct, so I want to put x plus ct downstairs over here. Well, that's easy enough to do, because I had that x was related to tau by cosh. Okay, I can relate that as a square root of 1 plus sinh. And I remember that sinh was related to t by just this formula over here. That gt over c was sinh of g tau over c. So that's the situation. So then I can write the distance between my rocket ship and my light, which they're running a race together. And I can see it's c to the fourth over c squared divided by x plus ct. I don't like x in there, but I can replace x by this formula for the position of the hyperbola as a function of t. And I do that here. I'm interested in what happens when t gets very large. Okay, when t gets very large, I can just tail expand the square root, and I can tail expand the reciprocal. Okay, routine things for me to do. Okay, and I can see that, and I can therefore calculate that x minus ct goes like a bunch of constants, like 1 over t. Okay, so the distance in the inertial frame between the point of the moving rocket ship and the light ray, it just falls like 1 over t. Okay. However, a simpler way to look at that, really, that's sort of complicated, okay, is that the invariant distance between the two is always c squared over g, right? This is an invariant hyperbola, okay? In other words, it's x squared minus ct squared is equal to a constant. If I take that to another frame, call it s prime, it becomes x prime squared minus ct prime squared is equal to the same constant, okay? It's the same old thing, okay? Okay, because that's an invariant, okay? And so the invariant distance between the two is always c squared over c, okay? Point B is related to A by a boost, okay? In the instantaneous rest frame of B, the distance to 0, 0 to the origin to c squared over g is c squared over g. That is, this looks like it's special, okay, to the rest frame, but if I go to point B, okay, and go to its rest frame, the picture is the same as this. Why? Because this is a light ray, it's invariant to the boost. This is a hyperbolic curve, it's invariant on the boost. When I do a boost, B comes down to C, and so the invariant distance between the light ray, okay, and the moving rocket ship that's experiencing a constant proper acceleration is always c squared over g. Okay, and that's the thing to understand. That's the thing to understand. That's the essence of the phenomena here. Okay, so next time, let's build on this and let's discuss how we can parameterize, okay, the wedge here, this whole space-time area, okay, between t equals 0 and x equals ct, okay, by a simple new parameterization, which will lead to a understanding of all of these frames which are moving in that particular way. So that'll be the next special topics that we'll do. It's called a Rindler wedge, and we'll pick it up next time. And you've got the basis for it now, and it's just a matter of a little bit of arithmetic, a little bit more analysis, and we'll understand something quite significant.